to the second lecture of Chapter 11 on liquids, solids, and intermolecular forces. So last time we talked about the different types of intermolecular forces, and today we're going to look at how that affects some of the physical properties of these substances. So the first of these is surface tension. And surface tension, you might be familiar with if you've ever tried to, fill up a cup of water and it gets really, really full and you think it's going to overflow, but then it doesn't. Or if you've done the experiment where you can see how many drops of water you can fit on a penny, right? And it's actually a lot. It's a crazy amount of drops of water on a penny. I think I've had students get like over 70 drops of water on a penny from a pipette before, which is crazy. But that's surface tension. So surface tension is the resistance to an increase in the surface area. And typically we see this with polar molecules, right? So they have dipole-dipole interactions, or even better, if they have hydrogen bonding. We will also see this with liquid metals. They have metallic bonding, which we're not going to cover much in this class, but it's another intermolecular force. So surface tension is resistance to an increase in surface area. So what that means is that instead of overflowing, your water glass might bubble over the top, or this penny, say this is a penny, will get us a lot of water on the top rather than having the water spill over. And so the reason for that is that these water molecules or other polar molecules are being attracted to other molecules that are under the surface. So like if we're looking at this molecule, whatever it happens to be, and it has maybe dipole-dipole interactions, maybe hydrogen bonding, both of which are fairly strong interactions. So it's attracted to all of these other molecules that are in there. And it's going to hang on to these other molecules. So rather than, spilling over the edge, this attraction between the molecules is enough that it kind of hangs on, and it will cause it to kind of bubble up. And obviously that only, lasts for so long. We have the ability to overflow cups of water and things like that. So here's a little bit more. So this first one, right, you couldn't float a paper clip on some water, and the reason for that is that the weight of the paper clip is not enough to break the surface tension of the water. The water molecules are still being attracted to each other, and so this, the weight of the paper clip is not enough to break that attraction and sink below the surface, so instead it kind of floats on the top. And for this reason, and for others, we say that liquid water kind of acts like it has a skin. Like this water bug here can appear to walk on the water. But again, it's not really, walking on water. Well, I guess kind of it is. But what's happening is that the water molecules are so strongly attracted to the other water molecules that the weight of this water bug is not enough to break the surface of the water and fall below it. So instead, it can kind of walk on top of it. So this is why a glass of water may bulge over the top. This is why water forms round drops in space. That's what they're looking at here. I know it's kind of hard to tell what they're doing, but this is a drop of water. And the water is attracted to the other water molecules. And so in space, there's no gravity to pull it down to the ground or pull it anywhere. So instead of breaking all apart, these water molecules, the strongest attraction they feel is to each other, and so they will essentially kind of hang on and will form these round droplets. And this is all because water hydrogen bonds. Water is a really, really cool molecule. And I know I keep saying that, but it is really extraordinary. So again, what's happening on the surface is that, each one of these molecules is attracted to the other molecules on the surface, but it's also attracted to all the other molecules underneath it. Okay. And so again, it has this tendency to hang on and resist a change in surface area. So hydrogen bonding, even though, or dipole-dipole interactions, it's more common that we see this with hydrogen bonding because it's a stronger interaction. But these interactions aren't happening in 2 dimensions. They're happening in 3 dimensions, right? And so even though we draw them in 2 dimensions on a paper, really they're 3D. And so each one of these molecules is attracted to all of the other molecules. So we see, under the water, it's attracted in all these different directions. But on top of the water, it's attracted to, other molecules that are on top and below. But it's not being attracted to anything, over the molecule surface. So it will have a tendency to stay with these other molecules rather than spilling over or changing shape, if it can. Obviously, once there's, enough of this water, right, that, you're going to really overflow your beaker or your glass or whatever it is, obviously it will spill over. So this is for kind of small changes in volume. But yeah, it's pretty cool. So the meniscus, we've talked a lot about, measuring from the bottom of the meniscus in lab. You hear that all the time, right? And the reason is because water is attracted to the glass. So, this is our glass, and the water molecules have some attraction, that's being shown in this bigger picture here, to the sides of the glass. So instead of just sitting straight across, it's kind of sitting on this curve where the water starts to creep up the sides of the glass. And here, so this is silicon dioxide that's being shown. And then the water molecules, are attracted to these through dipole-dipole interactions. And so it will start to climb, the walls of the of the tube, of the burette, of the graduated cylinder, whatever we're trying to measure it in. So we always measure from the bottom of the meniscus for that reason, to try and get as consistent of a reading as possible. These are called adhesive forces. And you can kind of think of it as like, because we have adhesive and cohesive, which we're going to look at in just a second. But adhesive forces, you can think about, we are adding another type of molecule into this mixture, which is making it, climb the wall. It's increasing that surface area, and it's creeping up the sides. Our other type of force is a cohesive force, where, like, if we had mercury in here, and I know it's kind of hard to tell, but if this was the sides of the glass, the mercury is not doing what water is. Mercury is doing this, right? It's got the opposite contact angle. And that is because the mercury has stronger cohesive forces than it has adhesive forces, which means that the mercury is more attracted to the other mercury atoms than it is to the glass. So instead, it kind of shies away from the glass, and it will try and stick together, whereas the water, like I said, was attracted to the glass and tries to creep up the sides. So we would read, the volume of mercury differently than we would read the volume of water, because it doesn't have the same contact angle. It's, making this convex instead of concave. And so we call this capillarity, or capillary action is a little more common. This ability to creep up or, shy away from the sides of the glass. So water... again, water is attracted to the glass, right? We have those adhesive forces. So we're seeing that water tries to creep up the sides of the glass. And if the more narrow our tube is, the farther and farther up the water will creep. And then the opposite is also true for mercury and these cohesive forces. Mercury is not attracted to glass, and instead it will try and shy away from it and stay with the other mercury atoms. And so when that happens, we get the opposite shape, and so the opposite is also true. The narrower that we make these, capillaries, the smaller and smaller the volume will be in them. So again, this is called capillary action or capillarity, but a little more common to call it capillary action. And the definition of capillary action is the spontaneous rising of a liquid in a narrow tube. The reason we define it as rising is that normally, normally we're measuring water or something similar to water. It's kind of more unusual that we're measuring mercury in one of these tubes. So the spontaneous rising of liquid in a narrow tube. But obviously, like I said, it can apply for mercury as well. It's just now it's the shrinking instead of the rising. Our next property that we're going to look at is viscosity. And liquids are fluid, right? They flow. You can pour them, kind of like gases or fluid. We can pour them, and they flow. But viscosity is the resistance to flow. So how, I think of it as how thick and syrupy is your liquid, like actual syrup, right? If you have syrup that you store in the fridge, I don't know why. I grew up storing my syrup in the refrigerator, and then I got married, and my husband is like, why do you store your syrup in the refrigerator? I have no idea. But we would always store it in the fridge, and it would get really, really thick, right? And the way that we would fix that is we would put it in the microwave before we would put it on our pancakes. I have no idea why we did this whole process. Not a clue. But syrup, when it's in the fridge, really thick, high viscosity. You can't really pour it. It's really syrupy. But if you stick it in the microwave for a little while, then it will become much thinner and it's easier to flow. So whenever you think about viscosity, I would think about syrup in the fridge or like molasses or something like that. But here's our example is glycerin. Sometimes it's called glycerol. It's the same thing. It's a liquid with really high viscosity. And in fact, you can't even really pipette this particular liquid. In order to pipette it, you kind of have to cut the tip off because it's so thick and syrupy. It like simply won't go up into your pipette. And so this is an example of really high viscosity. And high viscosity is an indication of strong intermolecular forces. So in this case, if we look at glycerin here, we have 3 different alcohol groups, 3 different hydroxy groups on the end, which is telling you that this can make a ton of hydrogen bonds, right? Each one of these can make, multiple hydrogen bonds with other glycerol molecules. So this is going to have really, really strong intermolecular forces because of all the hydrogen bonding. And essentially what happens is this thing gets kind of hydrogen bonded into place and it doesn't want to flow anymore because it's made all of these strong interactions. So the higher the viscosity is, that higher, the more syrupy something is, the stronger those intermolecular forces. So viscosity is the resistance of a liquid to flow. You can measure it, right? And so we've got some measurements here. These aren't super. There's particular instruments that you can use to measure the viscosity of something, which is where they're getting these numbers. Most times in class, or in lab, we would kind of just compare them more like this one flows easily, whereas this one doesn't. Stuff with high viscosity, like this glycerol, it is very, very clear that it has a high viscosity. But for more finite measurements, you can actually go through and measure it. But again, large intermolecular attractions will lead to larger viscosity. So if we look at all of these are all straight chain hydrocarbons. Pentane, hexane, heptane, octane, nonane, right? So we're getting longer and longer straight chain hydrocarbons. So like we were talking about before, the longer our hydrocarbons, right, and we're increasing our molar mass, which we said, usually corresponds to an increase in London dispersion forces, right? Not because it's got a higher molar mass, but because it has more electrons, right, and it's more polarizable. And again, as we get longer and longer chains, we're increasing the surface area that these chains can kind of line up and form these interactions, right? We talked about it last time, the bulky ones versus the straight chains, right? These are all straight chains. They're maximizing their interactions. So the longer straight chains will be able to interact even better. And they will have more electrons. They're more polarizable. So as we increase our molar mass, we're increasing the length of our chain. We are increasing our London dispersion forces. So if we're increasing our London dispersion forces, you can see we are increasing our viscosity, going down. So, but again, always walk through that whole line of thought, right? Don't just tell me, oh, it's got a larger molar mass, so it has a larger viscosity. No, not quite, right? Talk about the London dispersion forces, the ability to be polarizable, all of those kinds of things. This is what I was talking about with heating up the syrup. I don't know if any of you guys heat up your syrup. I have no idea where my parents got it from. But if you look, as you increase your temperature, right, then you are increasing. So these are all these different lines correspond to different temperatures. So as you increase your temperature, you are decreasing your viscosity. I guess that's a little bit hard to read in this particular graph, but that's what it's trying to show you. As you increase your temperature, you are decreasing your viscosity. It is becoming easier and easier to pour it. It's becoming less and less resistant to flow. All right, on to the next one. So this has to do with evaporation. So why does a glass of water lose volume when left out over time? So if you leave a glass of water on the counter for long enough, right, not for an hour or two, you wouldn't really notice a measurable difference in the volume. But over time, if you left it out, I don't know, say for a week, eventually some of these water molecules would start to evaporate and you would notice a decrease in the volume of water. Okay, so we know evaporation is the change from a liquid to a gas, but why is it happening at room temperature? We know water boils at 100, right? And so it's going to go from a liquid to a gas at 100 degrees Celsius. Well, it also happens spontaneously at room temperature. So what happens is that there's not as many attractions at the surface, right? We were talking about this with surface tension, that the molecules at the top are being attracted to nearby molecules and the molecules below. And at a given temperature, these molecules have a distribution of energy, right? They don't all have the same kinetic energy at a given temperature. There is the same average kinetic energy at a given temperature. That's how we actually define temperature, is an average kinetic energy, but that is an average, which means that some of the molecules have a higher energy than this average, and some of them have a lower energy than this average. So if we happen to have a really high energy molecule that's at the top of the glass of water, that molecule may have enough energy to escape. And then once it escapes, that escape will actually kind of cool the liquid a little bit, but over time, it will generate more high energy molecules, more low energy molecules, right? It will reestablish that temperature equilibrium, and then, hey, another molecule has enough energy to escape the surface of the water, right? Because it's got to escape all of those intermolecular forces. It needs to have enough energy to break those intermolecular forces and leave. But again, it's all because of this distribution of energy. Some molecules will have enough energy that they can escape, and over time, right, then another molecule will have enough energy to escape, and another molecule will have enough energy to escape, and so on and so forth. So that's why evaporation happens at room temperature, is because we are looking at a distribution of energy, not just they all have the same energy. All right. Vapor pressure. Vapor pressure is going to be one of our big topics for today. So we're going to start off by talking about vapor pressure by imagining a closed flask. We put some water in there at a constant temperature. There's no air at all. We sucked out all the air. It's under vacuum. And we just, like I said, half filled it with some water. Okay. So when the water is just added to the flask, it's capped. The water molecules, all of them, are in the liquid state. Over time, though, like what we were just talking about, some of those water molecules will have enough energy and they can escape the surface, right? And they go into the gas phase, and that will keep happening, right? It will, more molecules will have enough energy, they will escape, and they will go into the gas phase. And so at this particular time, we say that the speed of evaporation is much faster than the speed of condensation, because the opposite is also happening. Some of these gas molecules, again, average kinetic energy, right, will have less than the amount than they should and may condense back into our water, right? But initially, because there's nothing up in the gas phase, our speed of evaporation is much faster than the speed of condensation. But eventually, they reach the speed of evaporation, the speed of condensation reach the same speed. This is what we call an equilibrium, right? An equilibrium is established. And so the air in the flask, the space in the flask is now saturated with water vapor. It's holding as much water vapor as it possibly can. So for every one molecule now that goes into the gas phase, another one will condense back into the liquid phase. And so we establish an equilibrium. And at this equilibrium, the molecules that are in the gas phase, the vapor molecules, will exert some pressure on the walls of the container. If you think way back to when we studied gases, right, we looked at pressure through collisions. And so these gas molecules are obviously going to hit the sides of the container as they're bouncing around, and they will exert some pressure on the container. So the pressure that they are exerting, the pressure of the vapor molecules, this is called vapor pressure. Okay? And the vapor pressure, this is important. The vapor pressure is independent of the quantity of liquid. It does not matter how much liquid we have in the flask. We are just looking for the temperature. Vapor pressure is temperature dependent. As we increase the temperature, we are going to cause more of those molecules to have enough energy to go into the gas phase. And so we'll kind of shift this equilibrium so that more molecules are in the vapor phase, right, which makes our vapor pressure higher. The opposite is also true, though. If we cool it down, right, then we are causing less of these molecules to have enough energy to be in the vapor phase. So if there's less vapor molecules, then we will be decreasing the vapor pressure. So vapor pressure is temperature dependent. It doesn't matter how much liquid you have, right? It just matters what the temperature is. And it matters, what your stuff is. Is it water? Is it hexane? It matters those intermolecular forces. So you're looking at what is it and what's the temperature. So vapor pressure is related to the boiling point. And again, we know the boiling point of water is 100 degrees Celsius. But there, and we can look at the boiling points for other molecules, but the actual definition of boiling point is the temperature at which the vapor pressure equals the external pressure. So whenever the vapor pressure of your liquid equals the the vapor pressure of your substance equals the external pressure, then it will boil. It will go from the liquid phase to the gas phase. Your external pressure is typically atmospheric pressure. So that's, 760 millimeters of mercury or 760 torr or 1 atm or 101.3 kilopascals, right? No matter how you're measuring that, that's your atmospheric pressure. That's your external pressure, usually, most times. And here, so down here, it says the molecules in the interior of the water are moving so fast, right, at this particular pressure, at this particular temperature, that they can become gaseous, forming bubbles of gaseous water molecules, which can then escape and go into the vapor phase. But again, we're looking for the temperature at which the vapor pressure equals the external pressure. So that, thinking about that should allow you to answer this particular question then. Why does water boil at a lower temperature up in the mountains at a higher altitude? Well, what do we know about the mountains? Okay, so it's up higher, right? And if we are up higher, that means there is literally less atmosphere sitting on top of you, right? And so if there's less atmosphere sitting on top of you, there is a lower atmospheric pressure. Okay, at higher altitudes, the surrounding pressure, right, or our atmospheric pressure is lower. So therefore, the vapor pressure of our substance is lower. So therefore, the amount of heat energy needed to boil the water will be at a lower temperature because we're looking to get to a lower pressure, right? So our vapor pressure is lower, our atmospheric pressure is lower. So our stuff, in this case, water, will boil at a lower temperature because, like I said, atmospheric pressure is lower. So here is a kind of a typical graph. This is a vapor pressure temperature curve. Each of the curves represents different substances. So we have diethyl ether, ethanol, and water. Diethyl ether is held together by dipole-dipole forces, and then we've got ethanol and water, which can both form hydrogen bonds. So in thinking about that, diethyl ether, dipole-dipole forces, right, are weaker interactions than the hydrogen bonding in the other two. Keep that in mind as we talk about this particular slide. Okay, so you'll notice, looking at the graph before I talk about bullet points, there is a line up here at 760, and that's because we are in torr, right? This is atmospheric pressure, this line. And so this is going to be what we call the normal boiling point. When does it boil at atmospheric pressure, right? So when our vapor pressure equals our atmospheric pressure. So when the vapor pressure equals atmospheric pressure, right? When this is true, when our line hits 760 essentially, that temperature, if we go straight down, that would be our boiling point. And you can do that for each of these. So kind of like if we look at water, right, at 760, if we go straight across, on this curve for water, we will hit here, which is at 100 degrees, which is our normal boiling point for water. It may change based on, atmospheric pressure if you're, below sea level or above sea level, right? If you're much higher, up in the mountains, say, I don't even know, say we're here, right? Say we were at higher elevation, then you'll notice that water then would boil at a lower temperature. I know I just drew it to 100, but I think 100 is supposed to be farther over here or something. Who knows? But that's the whole point of this, right? Is that at a lower, for these curves, at a lower pressure, we would boil at a lower temperature. At a lower atmospheric pressure, we would boil at a lower temperature. So here, at any temperature, the vapor pressure observed is the highest for diethyl ether and the lowest for water. Okay, so I'm going to say that again. At any temperature observed, the vapor pressure observed is the highest for diethyl ether. So here's what that means. Diethyl ether, right, is held together by dipole-dipole interactions, which are weaker than the hydrogen bonds holding together ethanol and water. So that means that it is easier for diethyl ether to escape into the gas phase. Okay, so if it's easier, right, because it's not being held in the liquid phase by as strong of interaction. So if it's easier for diethyl ether to escape into the gas phase, that means more diethyl ether molecules will be in the gas phase at a given temperature. Okay, which means if there's more of those diethyl ether molecules in the gas phase, then there will be more collisions, so there will be more pressure. So at any temperature, vapor pressure observed is the highest for diethyl ether. So right here, high vapor pressure means low intermolecular forces. Okay, so they have, or weak intermolecular forces. And more volatile compounds, so this word volatile we haven't actually used a lot in this class, but volatile means that it is easier for your molecule to go into the gas phase. It's kind of talking about vapor pressure. How easy is it for your stuff to evaporate? So more volatile compounds have a higher vapor pressure because they have really, really weak intermolecular forces. So again, this is all coming back to intermolecular forces. If your substance is held together weakly, that means more of it can go into the gas phase, which means it has, it's more volatile, which gives it a higher vapor pressure. So also, right, more volatile compounds, ones that are held together more weakly, will then have a lower boiling point because, again, they're not held together by as strong of intermolecular forces. So here's another vapor pressure curve. Same kind of thing. You can go through and rationalize all of this out. So diethyl ether, like we said, that's held together by dipole-dipole interactions. We've got bromine, which is held together by London dispersion forces, which are actually, because bromine is such a large atom, it has a lot of electrons, and so those London dispersion forces actually end up being fairly strong. Then we've got ethanol and water, both with hydrogen bonding. We've got some more London dispersion forces in octane, ethylene glycerol, which we were talking about. It's related to the one we were talking about. Ethylene glycol is related to what we were talking about earlier, but you can see it's got two different areas where it can hydrogen bond. And then mercury, which can do metallic bonding. So if we were to look at this and see, okay, which one is held together by the strongest intermolecular forces, right? We would look at which one has the highest normal boiling point. And again, that's going to be at 760. So our highest boiling point would be mercury. So metallic bonds win here And then our weakest would be diethyl ether. Okay, but again, so you can look at vapor pressure curves to tell you a lot about the strength of the intermolecular forces. Ones that are more volatile, right, that are held together by weaker intermolecular forces, will have lower normal boiling points, but they will have a higher vapor pressure. Okay, at a given temperature, they will have a higher vapor pressure. So here's one. Which of the following is the most volatile? So which one is the easiest to evaporate, essentially? So again, we're going to look at which one of these evaporates or boils at the lowest temperature. So here I'm just going to draw it from 750 because that's close enough. So that's going to be our normal boiling point. And it looks like this one, which is ether, has our lowest boiling point, which means it has the highest vapor pressure, which means it will be the easiest to evaporate. Here's another one. Which of the following has the strongest intermolecular attractions? That one will have the highest normal boiling point. So again, we're going to go look at about 760. The highest normal boiling point would be this guy, which is titanium 4-chloride. Okay, and that one has ionic bonds, which makes sense. That's probably a solid, right? Here's another one. Which of the following has the highest normal boiling point? Again, normal boiling point, we are always looking at 760. So the highest normal boiling point would be titanium 4-chloride. So vapor pressure we can show as a function of temperature, right? Just like the curves we've been looking at. And it then tells us about the strength of the intermolecular forces. The higher that normal boiling point, the stronger the intermolecular forces. The lower the normal boiling point, the weaker the intermolecular forces, the higher the vapor pressure will be because they're less likely to be in the liquid phase. So lots of good things you can see from that. If you plotted the natural log of your vapor pressure versus 1 over temperature, you would get a straight line relationship. And you may be thinking, why would you want to do that? Well, chemists like to make things into lines, right? Just kind of in general, straight lines make us happy. We can calculate equations of lines, R-squareds, all that good kind of stuff. But the reason is that we can use this Clausius-Clapeyron equation. And so we have natural log of our vapor pressure. And if we multiply that by the negative enthalpy of vaporization over R times 1 over T, and then add in a C constant that changes based on what gas it is, right? You can write an equation of the line. You can think of this as, being your Y equals, this is all M, this is our X plus B, right? Equation of the line. So just a couple things, and then I'll talk about why we really care, right? P is going to be pressure. You can use this in torr, which is the same as millimeters of mercury, right? Or atmospheres. Doesn't matter. You could also use kilopascals. It doesn't matter which of these you use, because we are not going to use this particular equation or this particular version of this equation, and our units for our pressure are actually going to cancel out. So it doesn't matter which units you use, just as long as they match, as long as you are consistent. R is not the 0.08216, so be very, very conscious of that. This is not a gas law constant. This is our other R, right? That we use for thermo. So 8.314 joules per mole Kelvin. And I wanted to bring this to your temperature, or to your attention, that this is in joules. Normally when we report the enthalpy of vaporization, we typically use this in kilojoules per mole. But in this particular equation, since our R constant is in joules, you're going to need to convert this into joules per mole. So be careful there. T is T is for temperature, and you need to make sure that you have it in kelvins. Again, that is what our constant up here is telling us, is that we need to have it in Kelvin. And then C is a constant that depends on the gas, and in this particular equation, it depends on which pressure you're actually using. Are you using torr? Are you using atmospheres? Which one of those? This is not the version of the equation that we're going to use in this class. We have kind of a modified version of it, this 2-point form. And so it can be used to predict the vapor pressure if you know the heat of vaporization and you know the normal boiling point, because these are things that we can look up, right? We can look up the heat of vaporization, we can look up the normal boiling point, and so we can use this to find the boiling point at some other temperature, some other pressure, or if we know the pressure, we can find the temperature at which it boils. So here, very, very similar to the last equation, except now we have a ratio of pressures. So like I said, since we have this ratio of pressures, it doesn't matter what units you're using, torr, millimeters of mercury, atmospheres, kilopascals, doesn't matter, because it's going to cancel out. We're just looking for the ratio. So P2 over P1, just make sure you're consistent, make sure they're both the same. And then delta H of vaporization, or enthalpy of vaporization, you're going to need to put in joules per mole, not kilojoules per mole, which it will typically be given in. R is that 8.314 joules per mole Kelvin. And again, these temperatures, they need to be in Kelvin. And I've got a note here. Remember, the vapor pressure at the normal boiling point is 760 torr. So sometimes it will say something about the normal boiling point, or it will ask you something about the normal boiling point, and you're like, I need more information. Well, you have it. It's kind of like when we talk about STP, right? We know 1 atmosphere and 273, Kelvin and all that kind of good stuff. We know that the normal boiling point is 760 torr. So just keep that in mind. You may forget it. Let's do an example. So our problem is the vapor pressure of ethanol is 115 torr at 34.9 degrees Celsius. If the enthalpy of vaporization of ethanol is 40.5 kilojoules per mole, calculate the temperature in degrees Celsius when the vapor pressure is 760 torr, right? So we're looking for essentially the normal boiling point, right? Anytime we're looking for what temperature it's going to boil, right, our vapor pressure at 760, then we're looking for the normal boiling point. Here, it just went ahead and said 760 torr. So here's our equation from the previous slide. Natural log of P2 over P1 is equal to negative delta H vape over R times 1 over T2 minus 1 over T1. So first thing we need to do, we need to convert our temperature into Kelvin. So we'll add 273.15 and we get, our temperature there. So then we can go ahead and plug things in. Again, it doesn't matter if we're using torr or we're using, what units, whatever units are fine. So our new one, I usually put the old one, quote unquote, the one given in the problem that we're starting with as our, P1 and T1, and the one that we're trying to find as our P2 and T2. Obviously you could do it backwards. It will still work out just fine. Just be consistent. So natural log of P2 over P1 is equal to negative delta H vape. Again, make sure you change this into joules per mole, not don't leave it in kilojoules per mole. Then over 8.314, and then we'll multiply that by our temperatures. And again, make sure your temperatures are in Kelvin. So then if we simplify this, we'll get 1.89. So if we do 760 over 115 and then take the natural log of that, we're going to get 1.89. And then that'll be equal to negative 4870 if we divide these up, and that's going to be units of 1 over Kelvin, which is fun. And then we have 1 over T2 minus 1 over 308 Kelvin. Okay, so then I went ahead and divided both sides by negative 4870. So I get negative 3.88 times 10 to the minus 4 is equal to, and that's, yeah, I'm just gonna drop units. At the end, this whole thing's gonna come out in Kelvin anyways, so I'm just gonna drop units here. But if you want, this has Kelvin, and we've still got 1 over Kelvin on the other side. And then we've got 1 over T2 minus 1 over 308 Kelvin. So then I'm going to add 1 over 308 to both sides. Add 1 over 308 to both sides. We get, hang on, not negative. 2.86 times 10 to the minus 3 equals 1 over T2. And then I'm going to do 1 over both sides. And when I do 1 over both sides, then I'm going to get 350 is equal to T2. And then it wants our answer in degrees Celsius. So I'm going to go ahead and subtract 273 from that. And I'm going to get T2 is equal to 77 degrees Celsius. On these particular problems, because I know some of you are going to ask me, I'm not going to be grading you on significant figures because of the natural log stuff. We haven't looked at significant figures with natural logs. So I'm not going to grade significant figures on this section, so just kind of round how you see fit, and I'm going to look for us to get as close to the right answer as possible. And that is the end of this lecture. So we've covered a bunch of different applications of our intermolecular forces, and then, of course, we've learned this snazzy new equation. So go get lots of practice and send me any questions you have, and then I will see you next time.